structures is right in between this class and my break. So like if I go home, I may not come back. So.
Where do you live?
Not very far, only like 10 minutes away.
Okay.
Over by Divine Street, but I just don't want to.
That makes sense.
Maybe we'll get
Yeah.
lunch or something.
Yeah, that makes sense. How do you like your structures course? Is it hard or is it?
It's hard.
It's hard, yeah.
I missed this section just because I was kind of burnt out in that class on shear flow and torsion. Yeah. But then we did a problem Tuesday that was like heavily reliant on that stuff, and I got it. But so I was kind of confused. I was like, why do I understand this? Because I didn't pay attention for like a month. Like most stuff.
You didn't pay attention for a month?
Yeah, it was. Well, Darun's very lenient, and he said, you know, in his college experience in the Netherlands, he said, I don't really care what you do as long as you don't disrupt class, like do whatever. So I was like, all right, and then that gave me a license I shouldn't have had to not pay attention. And for whatever reason, I told Drake last Tuesday, I was like, I actually got that. It was like it was a boom problem. It wasn't a boom problem.
Okay.
I don't know why I understood it, but I did.
I mean, it makes sense. It all makes sense. It's just like the calculations.
Yeah.
I don't have to skip any more classes for materials. I
That's
have a
good.
75 test average, so I don't have to take the last test or the final.
Okay, that's good for you.
I'll be here for the rest of the semester.
We don't have that many lectures left, so that's
We have like 2 more weeks or something.
yeah, two more weeks, and the last day you have an exam. So including this lecture, we only have 4 more lectures, right? Today's Thursday, right?
Wait, so is our final on the last day of class?
It is on the last day of the class, yeah. Not the final, the exam 2.
Okay.
Exam 2 is on the last day of the class, yeah.
We have exam 2 then the final?
Yeah, yeah. If you want to move it, I'm fine. We can do it next Tuesday or next Thursday.
I don't know.
Okay. Yeah, I mean, if you like to move it, we can definitely do so. If not, okay. So we have finished the material for this course, and we have gone a little further than I really wanted to go. So, especially in the flight mechanics part. I wanted to, yeah.
Feels like the flight mechanics part of it was harder than the orbital.
Harder.
Or maybe more
Okay.
than kind of stuff.
I think I'm just a little more well-read on orbital mechanics. Had like a little bit of a decent understanding before we came in here. Flight dynamics, I feel like that's...
Flight mechanics, we only did like force balance things, right?
Yeah, but there's more like if blank, then include blank.
Okay.
Kind of situations, whereas orbital is just like this is just the way it is.
There's more variables in flight mechanics.
There are more variables. Yeah, that's true. Orbital mechanics. Yeah. So the plan. Let's actually talk about this, and then so the plan for the rest of since we are already done with the course material. The plan for the rest of the class is today we are going to solve some example problems because we didn't get to solve any example problems other than the last thing we did in the previous lecture for the orbital mechanics part. So we are going to solve some example problems, and today we are going to we have a very small part of chapter 3 that we have to talk about. A very small part of chapter 3 we need to talk about, and then we'll be done with chapter 3. My plan for the next 3 lectures is to do the interplanetary trajectories. But in order to understand the interplanetary trajectories, we need to have some prereqs. So maybe on Tuesday we do the prereqs, and then continue to do the interplanetary trajectories. Interplanetary trajectories is a little more complex. But if you have something in mind that you want to learn, or I'm of course open to suggestions or ideas. If there's something that you want me to focus on, you want me to go back to, or if you want to watch movies, just kidding, of course. I don't want to watch it. But
If we do the trajectory between two planets, would that be on the exam too?
yes,
And if we don't do it and just choose to review the stuff we've already gone over, will it still be there or will it not be there?
I mean, if I don't teach something, it won't be on the exam, right?
There are cruel professors.
There are what?
There are cruel professors that would put it on.
I want to learn it.
I
but
don't think so. Have you?
I want to learn it, but I don't want to be tested. What if it was a bonus, like this complex, like interplanetary?
It is not that complex. I mean, it depends. I mean, usually my perspective on complexity of the material is different, and vastly different from the student. So, let me put this: it really depends on you. If you want me to do this, we'll definitely go ahead and do it. If not, we'll think of something else. But we have to think of that other thing right now, right? But it will. If I teach it, it will be on the exam. Okay.
I'm going to vote for, last class we talked about like how whenever I had COVID was like the meat and potatoes of the orbital mechanics stuff. Like, I vote we do an example on that stuff.
Okay. We will do an example on all of those stuff today. Right? A couple of examples. Yeah.
I guess it's as many examples as we can fit in there before the exam.
Your your exam 2 is going to be easier than exam 1. So don't worry about the exam 2. Your exam, I will make sure you can finish the exam 2 in 75 minutes. Okay? That's no. That's so I'm thinking for the exam 2 and also the final. I want to make the final exam as short as possible as well. So maybe just 1 hour final exam. Okay? And for exam 2, I'll probably give you 3 or 4 problems, or 3 problems plus a couple of like short answer problems, multiple choice problems, right? And the solution, the answers to those problems will be just like 1 or 2 equations, not more than that. Just plug in this equation. I mean, not more 1 or 2 equations, but it will be like the examples that I'm going to solve today, but a bit shorter. Okay. So that is my idea for the exam 2. I'm trying to tone the exams down a bit because in my other classes, you guys did well actually compared to my other classes. So and your exam, let me put it this way, if I had to take this exam as a student, I would have gotten a 70, 75. So your exam, I thought your exam was a hard exam myself, but the other 2 classes was the easiest exams I could get. Yeah.
Coming back to in-person exams,
It is really nervous.
It is. Yeah, I agree. I definitely. It is a little weird, but I guess we have to get used to it, right? Your propulsion exams are gonna be tough. I mean, last semester it was easy because they had everything open to them, right? They could do it. They actually gave them a week for one of the exams.
we got to do it in person.
You have to do it in person. The class was in person, but the exam was not in person last semester. But yeah, and I was talking to Sang-hee the other day. He pushed me to make the propulsion even a little harder. So the material. Let me put it this way. Your knowledge as aerospace students is like 10 times more than the mechanical engineering students. So going out of this program, I can guarantee that you have learned as much as a Delft graduate. And Delft is the best school in the world, right? For aerospace. And I can guarantee that. Yeah, that's something I can guarantee. I put my name on it because, yeah, because I've seen what the material they cover. I mean, I.
Now I'm scared.
Why are you scared?
It hasn't been that hard yet. This has been like the first semester of like, oh, I've got to study.
You have been trained better than the mechanical students. Like I can see in mechanical, maybe because your class sizes are smaller or whatever. I don't know, but mechanical engineering students don't know anything. Yeah. No, it is the reality. I mean, like when your students don't know double integrals, don't know them, not that they can't solve them, don't know double integrals. Yeah, I mean, how that like senior students in a 500 level class. That's what I'm saying, yeah. Okay, so let's we still have to decide. Yeah, I don't feel like teaching today for whatever reason. No, today we're going to do a lot of examples, but we have to decide on what we're going to do for the rest of the class. And
Many examples under my belt.
I personally like to do the interplanetary flights, but it's going to be harder for me as well because I don't have that much of experience, right? I have to go back and reread a lot of material, and that, I mean, they have to come back to my memory, and my understanding is a little, my proficiency in the material is a little rusty, so I have to go back and reread the material a little bit. So, but I would like to do the interplanetary flight myself, but again, it is your choice. We have covered whatever we wanted to cover. The only thing that we haven't covered is the Gibbs method that was listed on the original syllabus, but the reason it was listed was because the person who was supposed to teach it before me originally, like 4 years ago, didn't know anything about orbital mechanics, just put down some names. That's it. I mean, when you haven't passed the course, you don't know anything. So I really didn't expect it. Yeah, so what do you think? Let's finish this discussion. Online people, I assume, I don't know if you're already commenting on this or not. You have one comment. The dude does not like us. Who doesn't? That dude does not like us. Us. No, Austin. He's talking about Austin. I guess Steven is an online student. That's why he's saying Austin doesn't like him. But no, he definitely likes you. Austin is a nice person. I like that guy. Yeah. But he's a bit strange. No, high standard. Yeah. That's a better word. Okay.
He's very lenient. Like he'll work with you.
Yep. That's correct. Okay, one interplanetary flight.
Yeah, I went to your office hours and I was like, are we learning interplanetary orbits? I mean, I'm just interested in it. I think it's the unit I was most excited for. So.
Okay.
It's on the exam.
Yeah. Don't worry about the exam. I mean, seriously, you shouldn't worry about the exam. You see what happened with exam 1. You didn't do well. It became a take-home exam. Your grade was between 85 and 100. We didn't have anyone less than. We had one. Huh? Pardon me?
I'm pretty sure I got a 75.
Yeah. Between 75. Because you didn't answer one of the questions, one whole question. So that was 20 points, right? But for people who answered all of the questions, we didn't have anyone less than 85. So don't worry about the exams. That's my point. So interplanetary flight, 2 votes. What about Igor and okay. What about Nirlev? We are talking about whether we want to do interplanetary flight or we want to do something else. Because we have finished the material we need to cover for this lecture, for this course, not just the lecture.
Let's talk about something easier.
Let's do something, talk about something easier. it is a little complicated. Yeah, you weren't here. I was telling you, everyone else that it is a little complicated. But so we have 3 votes for interplanetary flight, 1 vote against. What was your vote? More examples. 2 votes against. And this is not a unanimous vote. I want Stephen, and Stephen is only on the Stephen also jump in. More examples. 3 votes for it. Okay. Now we are. Who else are we waiting for? Witt and Emery. Emery left the class. Maybe he's on YouTube. No, he's probably on YouTube. On YouTube, there's like 30 seconds lag. Okay, so I guess it all goes back to how Witt and Emery are gonna vote, right? It is interesting. It is very interesting. Okay, and today is one of those days. I want to talk about your memories. Okay, so let's do this. One of you, Igor, as you are sitting closest to me, talk to Witt and Emery, ask about their votes, and let me know. Okay, but it has to be sometime today because next lecture is the lecture we want to start work on this. Okay, thank you. And today's bonus point went to Lawson and Trey. Okay, you didn't know we have bonus points for showing up early?
Oh, no,
Stephen also has. No, it will happen for the rest of the semester. Stephen was also here before 10:05. So, you came here early?
I wasn't earlier than that, though. Is it the first few people?
No, it is everyone who comes in before 10:05. You were here? Okay.
Does joining online count?
Joining online, yes. Yeah, you have to join before 10:05. Okay. So let's talk about. Let's finish this chapter. We will solve some example problems, and yeah, let's talk about universal variables. Okay. So if you recall, in the previous lecture, we talked about the mean anomaly of a hyperbolic trajectory. How did we define this? As mu squared divided by your angular momentum cubed, e squared minus 1 to the power 3/2 multiplied by your time. Okay. Let's see if we can change this at all. Let's see. What will happen to this term if I take a -1 out?
Or 1 minus e squared.
1 minus e squared. Exactly. Okay. To the power 3/2 t. Okay. And let's take this 1 out. It's going to be 1 to the power 3/2 mu squared divided by h cubed 1 minus e squared 3/2 t. What is this? -1 to the power 3/2. Pardon me? It does give us an not. Let's see. So -1 to the power 3/2 is -1 to the power. Let's actually do this like this. -1 to the power 3/2, right? That's it. And -1 to the power 3 is -1. So a square root of -1, which means that we are going to end up with an I. this is actually going to be a negative I. So just to make sure we take this negative 1 out, it's going to be negative 1 multiplied by the negative 1. It's going to be negative I. Okay. So this is equals to negative I multiplied by mu squared h cubed 1 minus e squared to the power 3 by 2 t. Go back to your notes and tell me, or if you remember, you can just tell me this. What is this part of the equation? What does this give us?
ME.
ME, exactly. So your hyperbolic mean anomaly is negative I multiplied by ME. Okay. So what does it tell us? This essentially tells us that all of these equations are very connected to each other. As long as you have these parameters that can connect the equations, you should be able to use some universal equations, right? And then get everything using these connecting parameters and those universal equations. But what are these? Let's see, how do they translate? Okay, so ME can be replaced by negative I, MH, right? In an elliptical orbit, elliptical hyperbolic. Okay. A semi-major axis in an elliptical is equal to negative A of the hyperbolic. Semi-minor axis is I multiplied by it, the imaginary number, and your E is equivalent to IF in hyperbolic. So the idea here is that we can replace all of these parameters as long as we have the, let's call it transfer factor, whatever you want to call it. So what is, yes?
I think the mean anomaly is switched. Should it be MH?
That's right. Okay. Let's do this. What will happen to this I if you take it to this side? 1 over negative I. What is 1 over negative I? Negative I to the power negative 1. Right? Let's see what happens here. What I want to do is to find a relationship between ME and MH instead of MH and ME.
So it's the same either way.
Can you calculate this for me? No, that's negative 1. Right? Is this something we can calculate? It is the same.
Yes.
It is the same. Okay. Okay. As I said, it's a very small part. We can actually, we have this section that continue the rest of this section of this chapter has come up with the universal equations, right? Just by giving you one equation, you can actually calculate all of the parameters for all of the different trajectories and orbits. But we are not going to go through those what we are going to do instead is just to try to compare the equations for elliptical and hyperbolic, and then we'll be done. And I'm going to ask you to tell me what the equations are. What is the orbit equation that gives us the true anomaly for hyperbolic and elliptical?
True anomaly?
Yep.
So that's 2 pi big capital T.
Orbit equation. That's R equals to the main orbit equation.
H squared over mu times 1
Okay.
plus e cosine theta.
This is for elliptical. What about the hyperbolic?
H squared over mu 1.
1 over.
Isn't that the hyperbolic one?
No, there's got circular.
So it's the same for all of them. It was a trick question, guys. Ah. Okay, so what about the equation of the orbit? For an elliptical one, you actually proved as a bonus point that this is the equation of the orbit, right? What is the equation of the orbit based on this thing that we have here for a hyperbolic trajectory?
This is just IB squared under the y and then negative a squared under the x.
Okay, so what will it be?
It'd be the same thing.
No.
X squared over a squared
Minus. Exactly. I to the power I squared is -1, right? It's not 1. Okay. What about the let's see, we have all of the other equations. Let me actually write the equations instead of asking you. Like the semi-major axis, we can calculate the semi-major axis as h squared divided by mu 1 minus 1 e squared for the elliptical. What does this mean? How can we calculate a for a hyperbolic? A has to become -a, right? So all of this will be multiplied by a -1. Right? And if you recall, the semi-minor axis was 1 minus e1 squared. For a hyperbolic trajectory is going to be e squared minus 1. The energy equation. What was the energy equation for an elliptical orbit? Who remembers?
Mu over h squared 1 minus e squared.
Can you repeat that?
Mu over h squared.
Mu over.
It's v squared over 2 minus mu over r.
Okay. It is equal to negative mu over 2a, right? What does this mean for a hyperbolic orbit? This was the energy equation, right? That was your kinetic energy, your potential energy, right? And then here we had mu over 2a, which was supposedly a constant value for every orbit, right? Yeah. Why is this a negative sign? It is for elliptical, though. You can't escape. So your satellite cannot escape the orbit yet. But it has to be a positive sign for your satellite to escape the orbit. And so on and so forth, right? We can do the same thing for the Kepler's equation. Me equals to E minus E sine of F, all of those things. Okay. Is there any questions?
Just
this A and B, semi-major axis. So in an ellipse, we have this is semi-major axis, this is semi-minor axis. Okay, and we have this idea in a hyperbola as well. Okay, okay. So let's that's it for the chapter 3. Let's start solving some example problems. Let's see where this example is. Yeah. Elliptical. So this is the example. We are given, we didn't solve any examples for elliptical orbit, did we? I remember I wanted to solve an example, but I don't think we ever had the chance to do so. Let's start with this. We have an Earth satellite as in orbit with a perigee. How do you pronounce this? Perigee or perigee? Perigee. Let's say perigee. Apogee and perigee. English is actually one of the easiest languages you can learn. Yeah. So, yeah. An Earth satellite. Okay, an Earth satellite is in an orbit with a perigee altitude of 400 kilometers and an apogee altitude of 4,000 kilometers. Okay, it is shown in a figure as well. We want to find eccentricity. Let's actually start with eccentricity. How can we find eccentricity?
We do ZA minus ZP over ZA plus ZP.
Okay, we have eccentricity. The correct equation is RA minus RP divided by RA plus RP. Okay. Well, what's the difference between Z and R? Yeah. How? That's correct. Z is the altitude from the Earth's surface, not the radius, right? So you have to, in order to get the radius, you have to add the radius of Earth as well. So just plug that in here. You're going to get ZE plus R of E minus ZA. That's RP minus RA. Doesn't matter.
The RE not cancel out when you subtract?
For the numerators, yes. But what about the denominator? That's it. Yep. ZP. And we are going to get ZA plus RE. ZP plus RA. Radius of the Earth is usually given to you. But in case it wasn't given, radius of the Earth is always 6,378 kilometers. Okay, so if you plug that in, did something happen? No. If you plug this in, what are you going to get? I have the final answer, so you don't need to calculate this. It's 0.298. So eccentricity of this orbit is 0.2, which means that we have calculated the correct eccentricity because we already knew this is an elliptical orbit, right? based on the values of ZA and ZP, right? And let's see if we can have any more understanding from this value of eccentricity. It's 0.2. It is closer to 0 than 1, right? What can you conclude from that?
It's less parabolic than it is. Sorry, yeah, it's less parabolic than it is elliptical.
Go ahead.
More rounder.
It's more circular, right? It's more circular than elliptical, right? It's more of a circle than an ellipse, right? Not more of a circle. It is very close to a circular orbit, okay? So next part of the problem is asking us to find the angular momentum. How can we calculate angular momentum? We have many different equations that you can use to calculate angular momentum, but we have eccentricity, and we also have R of P and R of A, okay? So what will happen to the orbit equation if I write it for R of P? The main orbit equation was h squared divided by mu, 1 plus 1 plus e cosine of theta, right? What is the value of theta at the perigee? 0, so cosine of theta is 1. And we have value of mu, that's 398,600 for Earth. We have the value of E, and we have the value of R of P, which means that we can calculate H to be 57,172 kilometers squared per second. Okay. The next part is asking us to calculate the perigee velocity, VP. How can we do this? How can we calculate the perigee velocity? The first thing you need to address here, because we know that the velocity here has two components, VR and V azimuthal, right? Are the both components present here when you are dealing with when you are trying to calculate the perigee or apogee velocity? How? What do you think?
I'm gonna say no. And
Can you elaborate?
does azimuthal factor in here? It does. Okay. Why?
What is azimuthal velocity?
I got the diagram.
Azimuthal is the velocity that is perpendicular, right?
Yeah. So is that the only one that's applicable?
Right. If you didn't have azimuthal velocity, if you had VR, it wasn't an orbit. It was just going away, right, on a linear path. But here, we only have azimuthal. Yes.
VP always the azimuthal?
Yeah. VR is 0 here, right? Okay. So how can we calculate V azimuthal, though?
H over R, or U over H1 plus E cosine theta.
H over RP would be the best, easiest equation to use here. And we have both H and RP. Okay? And we are talking about the azimuthal velocity at the perigee. At the perigee, so it is going to be 8.435 kilometers per second. Something that you need to keep in mind here is that we usually use kilometers here in orbital mechanics because meters is a small unit, right? Then you're talking about space. Okay. When you think of Earth as a very small object and something, the meters is a very small parameter. So you just have to make sure that you are consistent with your units, right? We always use kilometers. And the next part is asking us to find the apogee velocity, or V of A. How can we find that velocity? Again, it is at that point, we also only have azimuthal velocity, right? Not the same, no. It is not the same velocity. Look at the equation. Equation for azimuthal velocity is h divided by r. R is changing, right? So the velocity is not going to be the same. It's going to be h divided by r of A, which is going to be 5.509 kilometers per second. Okay. And part E of the question is asking us to find the semi-major axis. How can we find the semi-major axis in an ellipse? Right, we had it right here. You don't need to go back to your equation. Some of the concepts here are very easy to figure out. You don't need to go back to your notes. This is the semi-major axis, right? And let's say this is your focus. This is RA. This is RA. This is RP. So how can we find the semi-major axis? RA plus RP over 2, exactly. So you plug in these values that we have already calculated over there. It is going to be equal to 8,578 kilometers. The next part is asking us to find the period. How did we find the period of an elliptical orbit? We also had an equation for it. It was 2 pi divided by the square root of mu a to the power 3 by 2. You have calculated all of those, so your period is going to be equal to 2.196 hours. This equation calculates the period for you in seconds, but I just gave you the final value for you in hours. So it takes the satellite it takes 2.9 hours, 2.1 hours to orbit the Earth, okay? And we are also asked to find the true anomaly averaged radius. What was that parameter? True anomaly average radius. No. No. Those are mean anomalies. True anomaly was theta, right? That's the real anomaly, true anomaly. Not delta theta. That's true anomaly average radius. We are to calculate a radius, not a true anomaly. True anomaly average radius. R theta bar, right? So the hardest part of this orbital mechanics is to understand what you are asked to find, right? Because we have so many parameters that you don't really remember them, right? True anomaly average radius. We have RP, RA. Just plug in the numbers. And you will get 8,387 kilometers. 87 kilometers. Okay, and the part H is asking us to find the true anomaly when R is equal to R theta bar. Orbit equation, that's it. The general orbit equation is R equals to H over mu, H squared over mu, 1 plus 1 plus E cosine of theta. And we are just told that R is equals to R bar theta. You plug it in here, you have all of the other parameters, you find theta to be 96.9 degrees. 0.9 degrees.
In orbit mechanics, orbital mechanics, is everything typically in degrees? Or is it typically in radians?
Degrees. That, as far as I've seen, right? Yes, degrees. Yeah.
So is that 96.09?
0.09, yeah. Degrees.
If you got a square root of just RP on RA gives you average radius of the orbit.
True anomaly average radius, right?
True.
We had another type of average radius as well. That's a time average. We didn't talk about it. Don't forget. That's something I wanted to mention because I guess that's a time average radius. There's a time average radius. There's a true anomaly average radius.
How do they differ?
They differ based on the definition. That's an average radius. So for each true anomaly, you get that goes from 0 to 2 pi, 360 degrees, right? You find an average date for a time that's between 0 and some time, right? So it can be more than 2 pi, it can be less than 2 pi, just one time, okay? Let me actually give you this equation as well before we forget. The true anomaly average radius. We didn't talk about it, did we?
Well, we did time dependent yesterday.
No, time averaged radius. Just one, like R bar of T. Yeah. So R again, as just so you are clear, R bar of theta is the average radius for one orbit, right? R bar of T is the average radius for 0 to a specific time, right? It doesn't have to be a complete orbit. And these two are related. This is the equation. Just write this down. It's going to be A, 3, the semi-major axis, RT bar divided by A. Okay, so let's see.
So can you use R theta to find your, R theta to find your, the time in which it takes to, oh no, that's pretty, never mind. I was trying to think of how they put satellites in relays. They do like 1/3 of the orbit, put like a perfect triangle around a planet or Earth.
I'm not sure I understand your question. Okay. Okay. So part I. Yeah, there are many more that we haven't talked about the meat of the problem yet. What's that? This is, exam is going to be similar, but these are not very hard, are they? Just as long as you remember the equations, it's plug and chuck, right? The hardest parts are, I mean, not the more creative parts are coming up. So satellite speed. Satellites, we are also asked to find the satellite speed when r equals to r theta dots. Okay, how can we do that? There are many ways to do this. You can find the satellite, the different components of a speed, Vr and V azimuthal, but we can also use the energy equation. Energy equation for an elliptical orbit was mu divided by r equals to negative mu divided by 2a, right? And here we only have to put r theta. Mu we already know, v we already know, mu we already know. We can find the speed to be 6.97 kilometers per second. Okay. The next part of the question is asking us to find the flight path angle, gamma, then r is equals to r theta bar. How can we find the flight path angle? What was the equation? Who remembers that equation? Right? We had this equation for the flight path angle. Tangent of gamma is E sine of theta plus 1 plus divided by 1 plus E cosine of theta. This is something we saw in chapter 2 as well. We have already calculated theta for this r bar of theta. So flight path angle is going to be equal to 12.5 degrees. 12.05 degrees, yes.
Find the flat path angle when
R is equal to r theta. So the last part of the question is asking us to find the maximum flight path angle and the true anomaly at which this occurs. How can we do that? How can we find the maximum flight path angle and the true anomaly at which this occurs?
You just plug theta equals 1. Well, I guess that would be
Why theta would be 1? Theta equals to like 1 degrees.
wouldn't it be like just before one orbit is completed?
Why?
That would be the largest theta you could get would be like 350.
Flight path angle. We are talking about the flight path angle or angle of attack, whatever you want to call it, right?
so if the perigee amplitude would be the flattest, so that would be the lowest flight path angle. So would like a quarter rotation from either of those be the highest?
You have to be able to prove that, right? How would you prove that? What was the flight path angle? No. Not the value of it. You just the first thing you need to understand is what the flight path angle was. How, like, if I ask you what is the angle of attack, you will be able to answer me very quickly, right? Hopefully. What is the angle of attack? With respect to angle of attack is essentially your chord, the angle between chord and the free stream. That's the angle. That's how we define the angle of attack, right? For a simple two-dimensional case. But what is the flight path angle? We don't really talk about chords in satellites, do we? It's just these are point masses. Just think about it. What do you think the flight path angle would be? think a little. What are the different types of angles you have here? Theta, that's the true anomaly, right? That's the angle, yes. No, in orbital mechanics, what are the different angles we have in orbital mechanics? So, in an elliptical orbit, okay, you guys don't listen to me, all right? In the class. Okay, elliptical orbit, we have theta true anomaly, which is the angle between your apse line and R, right? At this location, R, we have two components for velocity, right? One is the VR, one is the azimuthal, right?
So when you have a phi angle two, that is the angle. That's weird. What about the angle theta in this case?
Just tell me what is the flight path angle. Don't just answer this question, then we'll go.
Between the tangent line and azimuthal.
Thank you. That's it. That's what we call the flight path angle. That's it. Okay. So that's the only angle that we are concerned with right now. At this point. Okay. The azimuthal, the angle between azimuthal and your tangent. And essentially your velocity vector, but the angle between your velocity. Okay. But the question is, how can I find the maximum here? I want to find the maximum of the maximum flight path angle.
Would that be at your semi-minor axis?
Why?
Your azimuthal velocity would be pointing directly up, and your tangent orbital path would be directly over.
Your azimuthal velocity will be pointing directly up.
Or down. Or your azimuthal velocity won't be equal to your other velocity vector. It won't be pointing straight up.
I mean, it doesn't matter. It's maximum.
Well, the minor axis, the anomaly is 90 degrees. So I would plug that in and you get large value.
Yeah.
It's not the mathematical case.
Okay, 90 degrees. What would you get when you put in 90 degrees right there? That's E multiplied by 0 divided by 1 plus cosine of theta, right?
That's the minimum, right?
What will be the flight path angle then when your tangent is 0? Your flight path angle will be 0. Or
No. Or 2 pi.
or I mean 2 pi, yeah. Or okay, so that's not correct. That's the idea.
So is it the quarter? Is the midway point between?
Just,
I still think it was the minor.
you know what? Be less engineers. Try to be a little more scientist. Okay? So don't look at the elliptical orbit. Look at the equation. I want to find the maximum value of gamma. How can I do that? We have a function. We want to find the maximum value of that function. How can I do that? I wanted to give you this example on the exam. I'm very happy that we are solving this. That's because otherwise on the exam.
I guess I think the graph is much values kind of make it like scrap it.
Okay. Let me. Okay. I'm 100% sure you know the answer to this. It's just you're just a little anxious now. That's why you can't answer this. We have a function, right? I want to find the maximum or minimum of this y or this f. What should I do?
Limit y to
Okay, you're getting warmer.
Take its derivative.
Take its derivative. What should happen? What? Yeah, exactly. So dx has to be 0, and then you find the value for x, right? Then you plug that value here into this function. You find the maximum or minimum, right? We call it x termum, right? It can be either maximum or minimum.
If we're talking about tangent, wouldn't it be maximum at 45 degrees?
How does tangent change with theta, with an angle? For sine and cosine, exactly. So for sine and cosine, we have, how does this change with theta? For sine, it starts from 0, goes to 1, and like this. But for tangent, you actually, at pi over 2, your tangent value is negative, is infinity. So this is how a tangent looks like, right? So there is no limit to the maximum value of a tangent. That's the idea here. Okay? So the only thing we really need to do here is to bring the tangent to this other side. Gamma is tangent negative of e sine of theta divided by 1 e cosine of theta. Okay? And we want to find the derivative of this function.
Wouldn't we do it with the respect?
I didn't hear you, huh? Let me.
I asked, do you want to find the derivative of arctan?
That's the idea. That's the inverse tangent, yeah.
Is it
1 over 1 plus tangent, right? So that it is. It's going to be 1 over 1 plus the value inside the tangent, not the tangent. E sine of theta, 1 plus e cosine of theta. The thing is, you don't need to take this derivative on the exam. You can just have it in your equation sheet and bring it, right? And then this is all multiplied by the derivative of this term with respect to theta, e sine of theta, 1 over e cosine of theta, right? Okay, this is this multiplied by this. And it is not that hard to take this derivative. Pardon me?
Quotient rule.
Yeah, that's just the derivative of e cosine of theta is going to be e cosine of theta multiplied by 1 plus e cosine of theta minus, it's going to be a mess, that's minus e cosine of theta. What's that? Divided by 1 e cosine of theta squared. And so this is all the numerator, this is the denominator, and this is all multiplied by this. And this has to be equal to 0 to give you the maximum. For this to be 0, your theta, you can simply, it is not going to stay this complicated and long. You can simplify this very easily, right? But for this to become 0, your theta has to be 102.1 degrees. So your maximum flight path angle happens at between in the second quadrants, right? Theta is going to be 102.1 degrees, which is going to give you a gamma of, let me see, what is the value of gamma we have here? Gamma of 12.11 degrees.
How'd you get that?
Well, in the third, multiple spots. I was only one, two.
Let me answer his questions first. What was the problem? What was the question?
How'd you get
You just set this to equals to 0, you get the value for it.
it? How'd you get
That's a lot of algebra.
Okay, let's do it. I guess let's see what Nicholas is asking and see.
I was wondering why it doesn't occur in multiple spots. Like, why don't you see one at, what is that, 12, so 78 as well?
Why don't you see?
77.9. Why, like, your theta is equal to 102.1, and that's supposed to be when your flight path angle is the highest. Why don't you see that in other spots as well?
Because your VR and V theta, those combinations are your velocity vector is changing, your azimuthal velocity, all of those things are changing. Yeah. That's the flight path angle is a direct derivative, if you will, of their velocity, right? Okay, so Igor is asking us to find a solution to this, and let's do it. The idea here is 1 divided by 1 plus e sine of theta divided by 1 plus e cosine of theta squared multiplied by e cosine of theta 1 plus e. Which one is wrong?
Said cosine and wrote down sine.
Which one is wrong? This is a sine. I just.
Yeah, I think there's supposed to be another one, so it's supposed to be sine squared because so that was, you take the low and you take derivative of the high and did that. And it's minus e sine theta derivative of 1 plus e cosine theta should be e negative sine. Instead of
That's
e
it.
cosine.
That this part multiplied by. Yeah, you are completely right. Thank you. So this is a sine. Yeah.
That should simplify that.
Yep. So let's do e squared. This will be a plus then. Sine of theta divided by 1 plus e cosine of theta squared. Okay, and this has to be equal to 0. Let's see if we can simplify this a little further. Here we have 1 plus e cosine of theta squared plus e sine of theta squared divided by 1 plus e cosine of theta. I'm just doing this in my head, right? This is going to be 1 plus e squared. Sine squared 1 plus e squared. Okay, so this side is going to be this side. Is going to be 1 plus e cosine of theta squared divided by 1 plus e squared multiplied by e sine of theta 1 plus e cosine of theta plus e squared sine squared theta divided by 1 divided by this 1 plus e cosine of theta squared. This is equals to 0, right? Which essentially means that this has to be equal to 0. So 1 plus e cosine of theta squared plus multiplied by e sine of theta 1 plus e cosine of theta plus e squared sine squared of theta is equal to 0. Okay? Which means that either this is 0 or this is 0. This whole thing is 0. Okay. We have sine squared 0. So this is either, so
Can you just treat it like a system of equations then at that point? Where you have both of them equal to 0 and find where they're both equal to 0?
it won't be a system of equations. You will have one acceptable or two acceptable solutions, or as many. So it won't be like, I'm not sure if I'm understanding your question right, but a system of equations is supposed to give you like 2 answers or 3 answers based on the number of equations you have, right? It's not going to be exactly like that. Let's stop here. I hope Igor accept this from us.
I'm a little confused on the first line at the top. If it's low d high minus high d low over low squared, wouldn't the first part of that second factor be 1 plus e cosine theta times e cosine theta? So did you, well,
That's right. That's right. That I have it e cosine theta here.
Okay, that was from.
Yeah. Yeah. It's a very line. Yeah. The thing is, no one is going to deduct any grade from me if I get this wrong, but you will lose points.
So is there a smaller equation for this, or a shorter way?
I would say let's, because this is something that you will probably get on an exam, right? You want to find the final value just as a parametric study of this theta, right? Because there's nothing, we didn't put any numbers here, right? So you can find the final and put it in your equation sheet, because these parts are not very important to me. What time is it? 11:19. Okay.
Well, not very friendly. What's the question number for this one?
That's question. This is the example 2.7. Example 2.7. Okay, so I guess we are still waiting for Emery and Witt to cast their votes. I think Witt joined us a bit late, though. You want to talk to your friends, Witt, and see what do you have to vote on. And Igor is agreed to let me know what your vote is. One more thing, your evaluations are going to be open. The student evaluations of the course, all of courses, of course, are going to be open on April 13th, which is going to be next Tuesday, right? I think so. Next Tuesday. Yep, next Tuesday. And whoever submits the evaluation and send me the receipt email, they send you an email that tells you that you have submitted the evaluation, will get a bonus point. I would prefer if you wait until the last day of the classes or the last day of the lecture. Last day of the class, doesn't really matter, before you submit, so you have a full overview of the course, right? And you can give me your ideas, your opinions. I'm pretty sure I will get all 5s. That I'm just kidding. But whoever gives me send me an email with the receipt of the evaluation will get a bonus point nonetheless. Okay.
If Witt and Emery also tie, can we flip the board?
No, then I will decide what I want to do, right? I guess I could have decided in the first place myself. Yeah, man. Flip a coin. Who would flip a coin for a course? That was the.
Someone who's taking another course at the same time as this one.
I'm done
I-
with it. I'm done.
Oh, yeah.
I
I don't really understand. We still have